So we've got a circle radius 6. So let's write that in here. We're going to try and inscribe this triangle in such a way that it maximizes the area. If that's a 6, then this dimension is also a 6 over here to that vertex. I'll draw in one more additional line down to the base, and I get something like that. That's a 6. I don't know what this is. This is going to be our variable. Depending on how far we draw this line, that's going to adjust the base and, of course, affect the area of the triangle. So let's call that an h. Yeah, 6 is given. Yeah, appreciate that. 6 is given in the problem. There's more than one way to do this. There's a way to do this as a function of angles. We're going to do this as a function of h, the distance from the center to the base. There's one more thing that I should label here, and that is the length of this side. How can I get the length of this side here? No, it's not necessarily. Well, we don't know that this is 6 anymore because it's not going to the center from the edge. So it's going to, the diameter, but not the center. Well, here's what we could do. We could use the Pythagorean theorem, right? That's a right angle. So the Pythagorean theorem would say 6 squared equals h squared plus x squared. 36 minus h squared equals x squared. So what's the length of this side then? Right here. What's it have to be? Square root of 36 minus h squared. And that's pretty good. I think we've got our picture labeled pretty thoroughly. There's not much more that I really want out of this. So that's our picture part. Let's turn attention to our function. For our function, we want to maximize the area of that rectangle, or excuse me, of that triangle. Let's start very simply though. What's the formula for the area of a triangle? Thank you. 1/2 the base times height. Now, in order to do this as a Calc 1 problem, we need to write that as a function of one variable. But we're pretty close to doing that, especially when we think about the length of the base. What's the length of the base? How far? Square root of 36 minus h times 2. Yeah, because we got 2 of them, right? 2 times the square root of 36 minus h squared. Nice. Well, because I got half of the base here, the other half is here, right? So this has to be square root of 36 minus h squared as well. So I got 2 of them, and that's the length of the base. And then I have the height is going to be this distance here, 6 plus h. What's nice is that this is now a function of one variable. Let's call it a of h. The 2 and the 1/2 cancel. I'll write it as h plus 6 times 36 minus h squared to the 1/2. Picture function interval. Interval is the next thing. Are there any restrictions on my choice of h?
Has to be positive and has to be less than the roots of 36.
All right, what's the square root of 36?
6.
Yeah. If it's beyond 6, then you're going to go past the circle, right? So it has to be between 0 and 6. I mean, technically, I guess it could be up here. H is negative, but you're not going to be maximizing anything there. So our interval is 0 to 6. It certainly can't go beyond 6 because you wouldn't have anything in terms of a triangle. As h gets closer and closer to 6, your triangle is going to be really, really, really narrow. And at h equals 6, you're just going to have a straight line. So 0 to 6 is our interval. Picture function interval analysis. Let's work on the analysis part next. What do you think we're going to have to do to try and maximize this area? Find the derivative. All right, so we'll start there. Find the derivative. So our analysis. Let me rewrite a of h. H plus 6 times 36 minus h squared to the 1/2. What rule or rules do we have to use to differentiate this? Product rule and the chain rule. Good job. So as far as the product rule is concerned, the derivative of the first is 1, differentiating with respect to x. So it's going to be 1 times 36 minus h squared to the 1/2 plus the derivative of the second. So that would be 1/2 times 36 minus h squared to the negative 1/2 times what? Negative 2h (1/2 minus 1). You're subtracting 1 from the exponent. Okay? But I appreciate the question. Lastly, times h plus 6. Let's clean this up a little bit. That's 36 minus h squared to the 1/2 minus h times, let's see, h times h plus 6 times 36 minus h squared to the negative 1/2. Okay, looking all right there. Is it or is it not? Let's see. Okay, yeah, it looks good. All right, let's keep going then. Do you recognize what's going to have to happen next? Yeah, that 36 minus h squared to the negative 1/2 term has to factor out. So when we do that, let's see what's left. Well, I have 36 minus h squared to the 1/2, and then h plus 6, 36 minus h squared to the negative 1/2. All that's going to get divided by that term out in front, 36 minus h squared to the minus 1/2. And I'm going to get a lot of nice simplification here. So those terms are going to cancel out completely. I get 36 minus h squared to the minus 1/2. Here, these exponents subtract. 1/2 minus negative 1/2 will leave me with a first power. Minus h times h plus 6. Okay, well, let's keep going. This term can come into the denominator. So what I'll be left with, I have a 36 minus h squared to the 1/2. In the numerator, this is going to be a minus h squared minus 6h. So overall, I'll have, let's see, minus 2h squared minus 6h plus 36. All right, so that's my derivative. I can clean this up a little bit, and maybe it's not a bad idea to do so. If I factor out a negative 2, that leaves behind h squared plus 3h minus 18, like that. So, wow. A lot of work there with the derivative. Let me pause there, give your hand a rest. If there's some problems along the way that I might have glossed over a little bit too quickly, let me know. Okay. I want to know where one of two things happens. I want to know where this is 0 or undefined. Now it's going to be 0 when the numerator is 0. It's going to be undefined where the denominator is 0. Where's the denominator going to equal 0? Yeah, negative 6 and 6. Are either one of them in our interval of interest? No. So nothing's going to happen there that we care about. So what we're going to work on then is where the numerator equals 0. So the numerator equals 0. Let's factor that. 2 times h plus 6 times h minus 3 equals 0. Okay. We get two solutions, h equals negative 6 or h equals 3. We'll throw out h equals negative 6 because it's not in our interval of interest. So the maximum area is going to be obtained when the height is 3, when h is 3. Let's see what that area is going to be then, because that's what the problem asks us for, is what's going to be the maximum area of that triangle. So we're going to go back here. A of h, our expression for that was h plus 6 times the square root of 36 minus h squared. So a of 3 is going to be 9 times the square root of 27. So 9 times 3 square roots of 3, or basically 27 square roots of 3. Yay. So that's the maximum area. If you want to be fancy, we should probably call that square units. Any wrap up or thoughts on problem 24 here? That's a good question. Is it the max or is it the min? There's a couple ways you could find out. I'm not sure I'd really want to employ the second derivative test here. So let me employ the first derivative test. So x, a prime. And let's look at the one that we care about, which is at 3. And let's test points on either side of that. So let's think. Such a point would be 1, or another point would be 4. Now when I put in a 1 here, I'll get negative 14 times negative 2. Well, a negative times a negative is going to be a positive. So it's going to be increasing. If I put in something to the right of 3, like a 4, 16 plus 12 minus 18, that's going to be positive, times negative 2 is going to be negative. So the function there is increasing, then decreasing. So what kind of point does that have to be? Yeah, it has to be a max. So h equals 3 is a max. Yeah, great question. Thank you. Let's move on and make ourselves a better world. Now, I'm 0 for 2 so far this season in asking this question. It looks like I'm 0 for 3. Does anyone have a can of pop on them? Like a 12-ounce can? You're going to go buy me one?
Yeah.
All right, put on my bill. All right?
I'm tired of you asking.
Well, yeah, I know. What's up with this? Well, it. I guess it. Well, I don't know. Aluminum is very recyclable. It takes a lot of energy to create aluminum, but once you got it, it's very easy to recycle. So, not sure. At least it doesn't require oil. In any case, what we want to do is want to minimize the surface area of a can. And the reason for that would be to minimize the material that you would need to construct it. So on the back of your handout, I've given you a can with some general dimensions, very simple ones, just H and R, right? The height and the radius. And our goal here is to minimize the surface area subject to the constraint that this is going to contain 22 cubic inches of volume. Now, what do you think that represents? The 22 cubic inches. That's 12 fluid ounces, plus a little space for some air at the top. All right, so it's about 22 cubic inches. Put whatever number you want here. The analysis isn't going to change much. So our goal is going to be to try and minimize the surface area. So that's it for our picture. There's not a whole lot there that I need to draw. So picture. And I've already labeled it for you too. How nice. What comes next then? Well, the function. Now the surface area is characterized in two ways. So there's two parts of the surface area. What are those parts? Any suggestions? What would those be? Nothing? Got nothing? If you're going to calculate the surface area, there's not any one formula that you're going to need. You're going to need to do it in a couple parts. What are some of those parts that you need to find the area here? All right, we're going to need the circumference. How about the lids on either end? What shapes are those? Let's be a little more mathematical. All right. Anyone want to go out and use a, there's a technical term, circle. There you go. All right, so we got a circle on top and on bottom. So what's the area of one of those circles? What's the area of a circle? This one I expect you to know. Area of a circle. Pi r squared. And we've got two of them, so we want the area of the lids is going to be 2 pi r squared. Now there's a little bit more that I need. Area of the lids, but there's a little bit more in calculating the area of this can, the surface area. What piece am I missing? All right, the height, but what is the height contributes to the area of what? Of the side. I don't know if that'd be plural or not. Area of the sides. It's kind of one side, but in any case, call it area of the side. Now here's what we're going to do in terms of calculating the area of the side. So here we go. I've got an amazing visual demonstration here for you. Here's our can. Wait. Let me make this a little bit better. All right. There's our can. That's better. It is St. Patrick's Day. So I want to find the area of the side here. And to make this easier, what I'll do is I'll cut this down the seam and unroll it. And when I do that, what kind of a figure is this now that it's unrolled? A rectangle. So how do you find the area of a rectangle? Length times height. All right. So it's going to be length times height. Now we already know the height here. The height is h, but the length is really going to come from the circumference of the can. So okay, how do you find the circumference of a can or circumference of a circle? I'll show you a little trick here. It's kind of cool. If you have the area of, for instance, a circle, then the way it changes as the radius changes is the derivative of this. And the derivative is 2 pi r. And it's changing at the circumference. So if you have the area, then you've got the circumference. And in a similar way, the volume of a sphere, which, not too many of us would remember, but if you had the volume of a sphere, 4/3 pi r cubed, and differentiated it, when you differentiate that, you're going to get a 4, because the 3's will cancel, pi r squared. And that's the surface area of a sphere. So, nice. Anyways, if you have one, then you can get the other. So this is going to be 2 pi r times h. And that's pretty good. That's not too bad for kind of a first glance at this. And what I would caution you with is not to try and get, the final form of this right off the bat.
They don't sell cans because you know how when they fall down from the machine it'll go. So I brought you coffee from.
Yeah. Thank you. You brought you coffee. All right. So there is a problem with this formula though, right? Can anyone see it? What's wrong with this formula as far as using it to move forward in a calculus problem in a Calc 1 class? 2 variables. Good. It's got 2 variables. So here's where we use the other part of what they give us. And I got to tell you, and it's not necessarily the best way to think about math problems, but it is something to keep in mind. If a mathematician gives you something in a math problem, chances are you're going to need it. 99.9% of the time, mathematicians don't waste words in their problems. They just give you the minimum of what you need. And here's one thing that they give you. This can is going to hold 22 cubic inches of volume. Now, what's the volume of a can? Well, take the area of the base, which is pi r squared, times the height. So there you go. Volume equals pi r squared h. And if you think about this, we actually know one of those variables. What would it be? Which one of these do we know? Yeah, volume is 22. And I can use that to solve for h. I get 22 over pi r squared, and that's h. So let's put that in to our formula right here. Let's see if we can't simplify things a little bit. So if I put that in here, I get 2 pi r squared plus 2 pi times 22 over pi r squared. And I think I'm going to get some simplification out of that. Yeah, the units of pi will cancel.
Wait, what happened to the r?
Oh, r's are still here. Thank you. R is still there. Only for a little bit, right? Because that r will cancel with one of those r's. And we'll get some more cancellation. Units of pi will cancel each other out. So that one and that one, those are gone as well. Thanks, Reem. 2 pi r squared plus 44 over r. That is our surface area. The nice thing about this is it just depends on one variable. It just depends on r. So let's call that S of r. Now the test that you just got back, a lot of you in working with some of your functions didn't make your life easier. For problems like this, instead of rewriting it, you use the quotient rule, which is like burning down a house to roast a pig. Okay, so let's try and make our life a little bit friendlier by rewriting that. 2 pi r squared plus 44r to the negative first power. I'm going to leave it there for the moment because I finally got my function kind of whipped into shape. What's the next step?
Find R terms.
Interval. Good. So the interval. What values make sense for R? What values can I put in that would make sense? Positive, yeah. Certainly you don't want a negative radius. Good luck building a can with a negative radius. So that won't work. So it has to at least be 0. Is there any natural boundary? Is there anything that limits you? Not really. Although it would be odd to have a can of more or less infinite dimensions, but there's no natural cutoff point like the previous couple problems. It's not like you can say, okay, you can't go past 6 or you can't go past 7. There's no natural cutoff point. I would expect something much closer to 0 than to infinity, though. So we'll work on that. Picture function interval analysis. So the analysis part here is going to start with s prime of r, which is going to be 4 pi r minus 44r to the negative second. And I want to know where that's equal to 0. Let me move that r or negative 44r to the negative second term to the other side. I'll get 44 pi r equals, not 44, how about 4 pi r equals 44 r to the negative second. In solving, let me note for you that r to the negative second really represents an r squared term in the denominator. Suggestions on how to solve there. Yeah, multiply both sides by the reciprocal. So let's multiply both sides by r squared. So I get 4 pi r cubed equals 44. I want to get rid of everything except the r's, so I get r cubed equals 44 over 4 pi, or better yet, 11 over pi. So the solution here then is going to be the cube root of 11 over pi for r. So that's your radius. Now there's an interesting thing here. Let's get a decimal value here. And this is something I didn't realize about this problem until I got the decimal value. The radius is about 1.518 something. The diameter, of course, is going to be twice that. So it's going to be about 3.037 is what I have as a decimal. But here's something kind of peculiar. If you calculate the height, remember the height is 22 divided by pi r squared, which is going to be 22 divided by pi times the cube root of 11 over pi squared. Yuck. You'd never know it until you actually do the decimal value. But the height is also 3.037. So what's strange about that? You got a square can. That's what you got. Looks like this right there. All right, I'll move this out of the way here so you can finish copying the problem. But a neighbor of mine a few years ago, World War II veteran, ironically, built this for me. It's supposed to be accurate to within 1/10,000th of an inch. He might be off by a little bit. Anyways, How come they don't build pop cans like that? I mean, it would save aluminum, right? There's two good reasons. One of which is you'd have to do a lot of retooling. I mean, all your machines would have to accommodate different size cans, etc. But even more importantly, as it comes around, you can feel it. It's not comfortable. It's the consumer's choice. They don't like cans that are that thick. It wouldn't be really fun to, sit back and relax with something that is so wide in your hands.
You know what else? They might have to retool a cup holder inside the cars.
Yeah, probably that. Yeah. Say again. That's a good question. Not sure. Not sure. But they have made a lot of engineering refinements, and the amount of metal that you need to produce 1,000 cans has shrunk from 36 pounds down to 28 pounds. So they have made a lot of improvements, and of course you can always recycle. In Michigan we have deposit laws, so you do tend to recycle. So that's a lot better. But yeah,
There's a documentary on Netflix that explains why the can is built the way it is.
really,
Yeah.
really, I'll have to check it on Netflix.
Yeah.
Really.
Like a half hour or an hour long. I can't remember exactly.
I think that the actual dimensions are the radius is 1.25 and the height is 4.875 are the actual dimensions of a pop can.
I've seen cans that are smaller than Pepsi cans.
Although it's like a shot. It's just, it feels like it's not even worth it. Yeah, I've seen them too. They're like,
They're so small and skinny.
yeah, they're crazy small. All right. Any questions on the math part, the calculus part, which allegedly we're all here for? But it's cool that you're interested in this the rest of the way. All right. Thank you. All right. To your health. Let's do a few more problems, and then I'm going to get you busy on some yourself. Problem number 22 is next on our list. Okay, so you've got a similar problem like this. I've drawn one like this on your handout so that you can do problem number 25. I've scaled it a little bit different, but it's the same idea. But kind of a nice warm-up to this one is problem 22. We're going to try and inscribe a rectangle inside of this triangle that fits neatly into the first quadrant. So the question is, what are the dimensions that maximize the area of that rectangle? Well, I mean, you could draw one shorter and wider. So we could draw something out here like this. So you get more width, but you're losing height. Similarly speaking, we could draw something with more height, but it's not as wide. So where's the place that maximizes the area here? Where along this line should I put this point? The midpoint? Depends. It's going to depend on the triangle. So we'll see. Well, I shouldn't be so cavalier in saying that. But let's approach it with some calculus, because it's not always going to be what you see as the most likely answer. Sometimes the answers do surprise you. So let's call this dimension, or call this direction x, this length. So how far we stretch it out this way. Now the problem itself gives you this equation, the equation of this line. I've only drawn it in the first quadrant. It's y equals 6 minus x over 2.
That's the hypotenuse.
Yeah, that's the equation of the hypotenuse there, yes. Now, if I wanted to list some coordinates here, I could list x and y. But let me see if I can't come up with something better than just a y here. What else could I put instead of y? right? The height. And what is that height in terms of x? Don't look too hard. Anyone? Anyone at all? Awesome. Thank you. 6 minus x over 2. Bonus points there, Shane. Well done. All right, so you've got these two are going to help us find an area in a minute. So picture function. Now our function that we're trying to maximize is the area here. That's just a rectangle, so the area is the length times the width. And let's see if we can't come up with a couple expressions for the length and the width. You could say an x and a y, and that's fine. But if we're trying to write this as a function of one variable, can I rewrite one of those? All right, what would y be instead of just a y? 6 minus x over 2. Excellent. And I'll write that as a of x. Or I could rewrite that as 1/2 6x minus x squared. Picture function. What's next? Victoria? Interval. Good. So what's my restriction on x? What can x go between? Yeah, 0 to 6. It has to be somewhere in here. Outside of this, you're not forming a rectangle anymore, not at least in the first quadrant. To the left of that, same thing. So between 0 and 6, that's our interval. So let's write that down here. Interval 0 to 6. Now I can't really include the endpoints here because on either endpoint, well, if I cut it out at 6, I'm not going to have any height. If I go down to 0, I'm not going to have any width. So it's not including the endpoints. So parentheses there. Picture function interval analysis. Now I saw a lot of people on the test working really hard to try and find some derivatives. But on this one, you really don't want to use the quotient rule. All right, this is just a polynomial. You have a constant out in front, so a of x is going to be the 1/2 times 6x minus x squared. But when you're differentiating, a constant doesn't really come into play. So just kind of look past that. Let's differentiate the 6x minus x squared. So a prime of that is going to be 1/2, and the derivative of 6x minus x squared, what is that? 6 minus 2x. And now if I want, I can distribute that and get 3 minus x. So that's not too bad as far as the derivative is concerned. What do I want to do now that I have the derivative? Set it equal to 0. Good. I want to find the critical points. So let's set that equal to 0. Can someone take out their graphing calculator and solve that one for me? Not all at once. Not all at once. All right, x equals 3. All right. Brave answer. Thank you. X equals 3. Let's take a quick look back at the problem and make sure we answer what they're asking. It says, what length and width should the rectangle be, or should the rectangle have, so that its area is a maximum? Well, a couple things come to mind here. First of all, is this going to be a maximum point or a minimum point? Does this maximize the function or does it minimize it? Am I going the wrong way? Am I getting the minimum area instead of the maximum area? Well, let's find out. And the way you can find out, there's a couple ways. You can use the first derivative test or you can use the second derivative test. But let me show you based on the second derivative test, because this is kind of relevant to, I don't know, a problem that you might have seen recently on a test. So here's our first derivative. 3 minus x. So a prime is 3 minus x. What's a double prime? -1. So it doesn't really matter where I look at this function, right? What's the shape of this function based on the second derivative? It's always concave up or concave down. It's less than 0, right? Something. Wait, timeout. Something looks wrong here. No, it's concave down. Concave down. Now, what's that mean is happening at our critical point? It means at our critical point, the function is concave down, so this has to be a maximum. Has to be. And that was the point of one of the questions on your exam there, was if you have the second derivative, your critical point when the function is concave down is a maximum. If you had something which was concave up, it'd be a minimum point. Okay, so this is a maximum. Let's find the actual lengths of these sides. So the length of one side is x, L is 3. The length of the other side is y. But when y equals 3, that width is what? Not quite 1/2. Yeah. 6 minus 3 is 3, so 3/2. So there's your length and width of the rectangle that maximizes the area. Nice, not so bad. I don't know. I don't think I'll be hitting this one on this one. Okay. So these are challenging problems. That's why I'm going to give you a little bit of time to work on it in class while I'm here. But let me give you one more before I do that. Is there anything else on 22 that needs a little help from me in order to help you first? Okay. Let's try problem number 16 then. It's kind of funny. A few years ago, the book had a slightly different version of problem 16. What they want you to do is try and find the point, let's call it x and y, on the curve y equals the square root of, I guess it'd be x minus 8. They want you to find that point that minimizes this distance here. What's the smallest that this distance can be? What point should you choose? Well, a couple years ago, instead of a point at 12,0, they put it out here at like 7,0, which is kind of silly, right? I mean, what point is going to minimize that distance? I don't know. Maybe this one right here. Done. End of story. So, I don't know. I kind of scratched my head on that, but they finally changed that in the current edition. So, I want to minimize this distance here. Let me take you way back to your algebra classes. What's the distance between 2 points? What's that formula? Square root of x2 minus x1 squared plus y2 minus y1 squared. All right, so that's what we need to minimize, that distance. And if I put in some stuff here, I can put in this point. We'll call that my x1, y1 down here at the bottom. And then this would be my x2 and y2. So that distance is going to look like this. X minus 12 squared plus y minus 0 squared. Again, just filling in the distance formula. Well, a couple things here. let's call this d. This is the square root of x minus 12 squared plus y squared. And I gotta confess that it took me a while to get used to this when I first saw this in a calculus class. We want to minimize this distance. Well, it's good enough to minimize the square of this distance. So if I square both sides, I get x minus 12 squared plus y squared. I want to minimize that. They're going to give us the same value. But can anyone see the benefit of going from one to the other? Why would I want to minimize the square of this as opposed to the distance? Yeah, get rid of the square root. It's a lot easier in terms of differentiating, solving, etc. Okay, there is one little bit of a problem here. Can anyone see it? What's wrong here? Yeah, you've got x and y. Jeremiah, any suggestions? What can I do to improve this situation? There we go. So we have y equals the square root of x minus 8. So let me put that in here. D squared equals x minus 12 squared plus the square root of x minus 8 squared. And that should simplify pretty nicely. I'm going to call this a different name because I don't want to differentiate d squared. The notation would get kind of ugly. So let's call that f of x. When I square this out, I'll get x squared minus 24x plus 144 plus x minus 8. Is it okay with you if I just simplify that and give it to the final? Well, I'll do two steps. X squared minus 24x plus 144 plus x minus 8. And when you combine like terms, we get the final function here, x squared minus 23x plus 136. Okay, picture function. So that's our function. Here's your picture. Now comes the analysis. No, wait, not yet, not yet. Can't do the analysis yet. What else do I got to do first? Interval.
Yeah, but what happened to the d squared?
I just chose different notation for it. I just said, you know what? Let's just call that f of x as opposed to the d squared.
Okay.
Just because I don't want to have to differentiate. I don't want to come up with notation for the derivative of d squared with respect to x. It just would look ugly.
Something with it later on, right?
No, this is this. D squared simplifies down to this. So if you'd like, we could call this d squared. Here, I'll write it here. D squared. There you go. For you. There you go. All right. she started copying that. Okay. So what about our interval? What values can x be? Can x be just anything? What's the limits on x? Yeah, x can't go below 8, right? Because otherwise you're not on your parabola anymore, or this half of a branch of a parabola. So 8, and then there's really no limit here, although I don't suspect it's really going to be much past 12 or 13 at all. But 8 to infinity. That's our interval. Picture function interval analysis. All right, so A f of x was x squared minus 23x plus 136. Let's work on the analysis part. F prime of x is 2x minus 23. And when I set that equal to 0, I get x is 23 over 2. Or you could write 11.5. That's fine. Now if x is 11.5 or 23 over 2, let's see if we can't figure out what y is. Y is going to be the square root of x minus 8. So 11.5 minus 8 is the square root of 3.5. I'd be very happy with that. Don't bother giving me a decimal value, just leave it like that. You could also write it as 7 halves. The book would probably rationalize the denominator and give you something like that. Any of these three would be fine. I'm not going to worry about too much. So overall, the final coordinates would be 23 over 2 and square root of 14 over 2. Or any one of these other equivalent ones. Any wrap-up thoughts for problem number 16? If you notice, it looks reasonable. Your answers should look reasonable. When you look back at them, you look back at your drawings, etc. This should make sense. So for homework, try problems 3 through 25 and 35. Boy, there's a lot more there. I should probably keep going, right? Let's see what these go all the way up to. Wow, 55. No, just kidding. That's good enough here. Nothing else to wrap that one up?